The diagram in the top left box shows the arrangement of electrons in atomic orbitals for a carbon atom and the shapes of these orbitals. The third p orbital shape has been drawn with a dotted line because this orbital is not occupied. From this diagram, it would appear that there are only two singly occupied p orbitals that are able to form covalent bonds. However, we know that methane, CH4, has 4 covalent bonds. Now you will learn how this can be explained. Before forming covalent bonds with 4 hydrogen atoms, the carbon atom undergoes hybridization. One of the 2s orbital electrons is promoted to the empty 2p orbital. Click the forward button to see this in the bottom left box. Next, the 1 singly occupied 2s orbital and the 3 singly occupied 2p orbital hybridize to form 4 new Sp2 hybrid orbitals. Click the forward button to see this happen. Why are the new hybrid orbitals called Sp3? Answer: they have been formed from 1s orbital and 3p orbitals. The 4 Sp3 hybrid orbitals occupy an energy level between that of the 2s and 2p atomic orbitals. The diagram also shows the shape of each of the 4 Sp3 hybrid orbitals. How is this shape different from the 2s and 2p orbitals from which they were formed? Answer: the shape is neither a sphere nor a dumbbell. It is like a dumbbell but with unequal halves. Since there are 4 identical Sp3 hybrid orbitals, the arrangement of these orbitals is tetrahedral. The diagram in the larger box shows the shape and arrangement of the 4 carbon atom Sp3 orbitals together with 1s atomic orbitals of 4 hydrogen atoms. The carbon atom can now form 4 covalent bonds as the hydrogen 1s and carbon Sp3 orbitals overlap. Click the forward button to see the orbitals overlap. Note that in the bottom left box, the molecular orbitals now contain 2 electrons each, one from the carbon, a black arrow, and one from the hydrogen, a red arrow. Select Ball and Stick from the menu to see a ball and stick diagram of the methane molecule. Move your cursor across the diagram to rotate the structure. What is the angle between any two of the covalent bonds in methane? Answer: the tetrahedral angle of 109.5 degrees. You have seen that Sp3 hybridization can occur in a carbon atom, but Sp3 is not the only type of hybridization. and hybridization can occur in other elements. The diagram in the top left box shows the arrangement of electrons in atomic orbitals in a beryllium atom. The shapes of occupied and unoccupied atomic orbitals are also shown. Beryllium can undergo sp hybridization. One of the 2s orbital electrons is promoted to an unoccupied 2p atomic orbital. Click the forward button to see this. The singly occupied 2s and 2p orbitals then form two new sp hybrid orbitals. Click the forward button to see this. The sp hybrid orbitals of beryllium will have a linear arrangement. The large box shows a diagram of these orbitals, together with the 1s atomic orbitals of two hydrogen atoms. The sp and s orbitals overlap to form covalent bonds. Click the forward button to see the orbitals overlap. Note that in the bottom left box, the molecular orbitals now hold 2 electrons each. One from the beryllium atom, a black arrow, and one from a hydrogen atom, a red arrow. What shape is a beryllium hydride molecule? Answer: linear. Select ball and stick from the menu to see a ball and stick diagram of a beryllium hydride molecule. Again, move your cursor over the diagram to rotate the structure. What is the angle between the two covalent bonds? Answer: 180 degrees. You have seen examples of sp3 and sp hybridization. It is also possible to get sp2 hybridization. The diagram in the top left box shows the arrangement of electrons in atomic orbitals for a boron atom, together with the shapes of these orbitals. Think of how hybridization can take place in this atom. What will be the first step? Click the forward button to see this in the bottom left box. What will happen next? Click the forward button to see this. The boron atom shown in the bottom left box now has 3 sp2 hybrid orbitals. The big box shows the arrangement of the sp2 hybrid orbitals, together with the 2p atomic orbitals of 3 fluorine atoms. How are the 3 sp2 hybrid orbitals arranged around the boron atom? Answer: in a trigonal planar shape. Click the forward button to see the boron and fluorine orbitals overlap. Note that in the bottom left box, each molecular orbital now has 2 electrons, one from the boron atom and one from a fluorine atom. Select ball and stick from the menu to view a ball and stick diagram of boron trifluoride. Move your cursor over the diagram to rotate the structure. What is the angle between the covalent bonds? Answer: 120 degrees. Summary: hybridization is the mixing of at least two non-equivalent orbitals, for example, s and p orbitals. Hybridization allows some atoms to form more covalent bonds than the number of singly occupied orbitals in the atom would suggest. The number of hybrid orbitals produced is equal to the number of orbitals that are involved in the process of hybridization. Depending on how many singly occupied p orbitals average with the singly occupied s orbital, there are three types of hybridization. The three types of hybridization, sp, sp2, and sp3, form respectively 2, 3, or 4 hybrid atomic orbitals. The hybrid orbitals form covalent bonds when they overlap with the orbitals of other atoms.